Hello everybody, welcome into another lesson. So today we are going to talk about properties of logarithms. So the first property we want to talk about is called the change of base formula. This is going to come in handy when you go to try to calculate the value of logarithms. So if you have some log base a of x, you can convert this to some log base b of x divided by log base b of a. So it's always going to be the log of the base that you desire of that x divided by the log of the base that you desire of the base of the log that you started with. Now, when you put this into a calculator, you really only have two options. You have the common logarithm, which is base 10. In your calculator, it would just appear log x over log a. So log base a of x, you can convert this into log base 10 of x over log base 10 of a, which is log x over log a, because your calculator for the log is set for base 10. You can also do it as a natural log. Log base a of x equals the natural log of x over the natural log of a. It really doesn't matter what base you pick that you want to convert it to. Your calculator will do it either with the common log or the natural log. So that's how you would do change of base. Let's do some examples here. We're going to take some logarithms. We're going to round the result to 3 decimal places. So let's find some good examples. So let's say we're given log base 3 of 7. So we're going to be given log base 3 of 7. I'm going to first do this with the common logarithm, and then I'm going to do it with the natural logarithm. And we should arrive at the same answer. Just to prove it doesn't matter what base you desire to change it to. So if you wanted to input something like this into your calculator, if we're going to use the common logarithm, use the common log, this log base 3 of 7 would be equal to log base 10 of 7 divided by log base 10 of 3, which in your calculator you'll only see log. It's by default set for base 10, so you would input log 7 over log 3. So let's go ahead and get an answer to about 3 decimal places. Let me just bring up my calculator. Whoa, didn't want that. I get about 1.771. So the answer you should get is approximately 1.771. I can also do this with a natural log. Again, it does not matter what base I pick, it's just that your calculator is only either set for the common log of base 10 or for the natural log of base e. So log base 3 of 7 is the same as the natural log of 7 over the natural log of 3. Now let's go ahead here and put that into the calculator, and we should come up with about 1.771. And what do you know? Yep, you come up with approximately 1.771. So either way, you're going to arrive at the same answer. Now for the rest of these, we'll only use the natural log. I find it easier to use the natural log. And when really it's no easier or no harder. I just prefer to use the natural log, but there's no right or wrong one to use. Now, let's take log base 7 of 4. So we're going to do log base 7 of 4. This is going to be the same as the natural log of 4 divided by the natural log of 7. So we should be able to get a result to approximately 3 decimal places. It should give you about 0.712. So the answer I should get is approximately 0.712 for that answer. Let's do a couple more of these. Let's say I want to do log base 9 of 0.8. So I'm going to evaluate log base 9 of 0.8. Well, that's the same as the natural log of 0.8 divided by the natural log of 9, which now we should be able to pull up an approximate result to 3 decimal places. Which should give us about negative 0.102. So negative 0.102 should be the answer we get for this. And yes, sometimes you will end up getting negative answers. That does sometimes happen. I got one more. Let's say we have log base 30 of 135. So log base 30 of 135. This is the same as the natural log of 135 all over the natural log of 30, which now we can put those into the calculator and get an approximate 3 decimal place result. We get approximately 1.442. So the answer we should get to 3 decimal places is approximately 1.442. Alright, so there's your change of base formula. That one's pretty easy. Now, there are 3 other useful properties for evaluating logarithms. So there's the power property, which we actually talked about yesterday, but it's going to be reiterated today. We have the power property that states if you have the log of some base of a number to a power, so if I have log base a of x to the n power, what I can do with that power is remove it from the exponent, bring it down in front of the logarithm, and multiply it by the logarithm. So that log base a of x to the n equals that n times log base a of x. That's a very useful property. Then there's 2 more we could talk about today. There's also the product property. So the product property of a log is, let's say I have log base a of xy. So in parentheses, I have 2 different numbers that are being multiplied by each other for the logarithm. So log base a of xy. This is the exact same as taking the log base a of x plus log base a of y. So I can rewrite that product as the sum of 2 separate logs of the same base. And then we also have a quotient property. which all three of these are going to come into play in the subsequent exercises we're going to do. So let's say I have log base a of the quantity of x divided by y. So this time I have log base a of the quantity of x divided by y. Well, the quotient property of logarithms states that I can take that log base a of x minus log base a of y. So a quotient of you have a quotient of two numbers inside of one logarithm becomes a difference of two logarithms of the same base. So these three properties are very important for dealing with logarithmic expressions and will also be useful when we go to solve logarithmic equations in the next lesson. So let's do some exercises here. We are going to expand the expression. Actually, we're not even going to do that first. Let's use the power rule and get a number. So let's say I have something like log base 4 of 8. How can I simplify that to get a number? Well, what is 8? Isn't 8 the same as 2 to the thirds? This is the same as log base 4 of 2 to the thirds, right? So, because 2 to the third is 8, well, what do we know about the power property of logs? That power can come down front. So, this is going to be the same as 3 times log base 4 of 2. Now, log base 4 of 2, okay, so 4 to what power equals 2? Well, we know the square root of 4 is 2, so that'd be the 1/2 power, right? So this would become 3 times a half, which should just give you an answer of 3/2. It would simplify into 3/2. And it's true, if you take 4 to the 3/2 power, you would get 8. Alright. Let's say we have log base 2 of the quantity of 4 squared times 3 to the 4th. So how are we going to handle that? We have a couple things going on. You have a product and powers inside of your parentheses. First thing you probably want to do is use the product rule. So log base 2 of the quantity of 4 squared times 3 to the 4th. So use your product rule first. This would be the same as log base 2 of 4 to the 2nd plus log base 2 of 3 to the 4th. Now, on each of these we can use the power rule. So the next thing you should get is 2 log base 2 of 4 plus, then you'll bring down that 4 for your second term, you'll get plus 4 log base 2 of 3. So let's look at this here. What is log base 2 of 4? That's going to be 2, right? So we'll end up having 2 times 2 plus 4 times log base 2 of 3, which would end up giving you 4 plus 4 log base 2 of 3. And that's as far as we can go if we want an exact answer. We could always get decimal answers if we want, but you would end up getting 4 plus 4 log base 2 of 3. That would be the best you could do with this. 2 more of these. Alright, so we have the natural log of the quantity of 5e to the 6th power. So we have the natural log of 5e to the 6th power. Well, we have a product rule to start with, so this would turn into the natural log of 5 plus the natural log of e to the 6th. Well, on the second term you have a power rule, so this can be rewritten as the natural 6 times the natural log of e plus the natural log of 5. Now, what is the natural log of e? So e to the what power equals e? That would just be 1, right? So what you should end up with in the end is 6 plus the natural log of 5. And that's the best you could get. If you want an exact answer, we could get decimal answers, but this is the exact answer, 6 plus the natural log of 5. Last one of this. Alright. We have the natural log of 6 all over e squared. So we have the natural log of 6 over e squared. Well, you have a quotient rule this time. So how this can be rewritten is the natural log of 6 minus the natural log of e squared. And again, on your second term, you have a power rule, so this will turn into the natural log of 6 minus 2 times the natural log of e. Natural log of e is just 1, so in the end you should just get an answer of the natural log of 6 minus 2. So your answer you should get is the natural log of 6, all that minus 2. So that's how you do this with numbers. We're going to expand some variable expressions. So we are going to expand the expression. Then after these exercises, we'll do some condensing. We'll work in reverse. So we're going to expand the expression here. So let's say you have log base 10 of 5x. So we want to expand this. Log base 10 of 5x. Well, you have a product of two numbers inside the logarithm. This would just be the same as log base 10 of 5 plus log base 10 of x. And that would be the best you could get. This would turn into log base 10 of 5 plus log base 10 of x. Easy enough. Now, on the other hand, let's say we have log base 10 of 5 divided by x. So we have a quotient rule. We have log base 10 of 5 divided by x. So this would be a difference of two logs. This would turn into log base 10 of 5 minus log base 10 of x. And that would really, honestly, truly be the best we could get. This would turn into log base 10 of 5 minus log base 10 of x. Alright, log base 8 of x to the 4th. So we have log base 8 of x to the 4th. Well, all we have going on here is a power rule, so this would just turn into 4 times log base 8 of x, and there's really nothing else we can do with it. So you would just get 4 times log base 8 of x. Alright, now what if we had the natural log of the square root of z? Well, what is the square root of z? Isn't that the same thing as the natural log of z to the 1/2 power? That would be the exact same thing, right? So you have a power rule. This would just turn into 1/2 of the natural log of z. And that's really all you would get. 1/2 of the natural log of z. Now, how about this one? We have the natural log of the quantity of x, y, z. So we have 3 products inside the logarithm. Well, the product rule still holds true. this is just going to be three separate sums. This would turn into the natural log of x plus the natural log of y plus the natural log of z. And that's all this would turn into to expand it. The natural log of x plus the natural log of y plus the natural log of z. And spice it up a bit. We have the natural log of 3, natural log base 3 of a squared b c to the third. So we have three products inside the parentheses. So having said that, let's treat this as the product rule first, which what does that really mean? That means the sum of three separate logs, right? So this would start out as log base 3 of a to the second plus log base 3 of b plus log base 3 of c to the third. Now, on the first and third term, you have a power rule. So this could be expanded further into 2 times log base 3 of a plus log base 3 of b plus 3 times log base 3 of c. And that would be the best we could do. 2 log base 3 of a plus log base 3 of b plus 3 log base 3 of c. All right, another one here. So we have the natural log of the quantity of a squared times the square root of a minus 1, where they give us that a is greater than 1 as part of the domain of logarithms, okay? So in here we have a product rule. This could be the same as the natural log of a squared plus the natural log of the square root of a minus 1. Well, let's deal with that second term. We'll leave the powers in place for a minute. We have the natural log of a squared plus the natural log of the quantity of a minus 1 raised to the 1/2 power, right? Now on each of these terms you have a power rule. So this would turn into 2 times the natural log of a, not 2 times la, 2 times the natural log of a plus 1/2 times the natural log of the quantity of a minus 1. And that would be your simplified answer. 2 times the natural log of a plus 1/2 times the natural log of a minus 1. All right. Now, we have the natural log of the cube root of x divided by y. So we have the natural log of the cube root of x divided by y. Well, we know for sure this is the same as the natural log of the cube root of x over the cube root of y, right? Now let's take this further. Cube root is the same as the 1/3 power, right? So this would equal the natural log of x to the 1/3 power over y to the 1/3 power. Now we've truly got this as a quotient rule with logarithms, which means the difference of two logs. So this would become the natural log of x to the 1/3 minus the natural log of y to the 1/3, which now you have a power rule. This would turn into 1/3 times the natural log of x minus 1/3 times the natural log of y. And that would be the best we could do. 1/3 times the natural log of x minus 1/3 times the natural log of y. Got two more expandings. Okay, so we have the natural log of x squared minus 1 all over x to the third. They also give you in this case that x is greater than 1 just so you don't end up with a 0 inside your logarithm. Well, there's a couple things we got to discuss here. First of all, we can factor x squared minus 1, right? Because the goal is to expand this. This would actually turn into the natural log of the quantity of x plus 1 times x minus 1, still all over x to the third. Now, you have inside the parentheses, you have both a product and a quotient rule. Well, what does that mean? For your numerator, you can write this as the sum of two natural logs. This would be the natural log of x plus 1 plus the natural log of x minus 1. Now, you have a quotient. You have the denominator of x to the third, so this would end up becoming minus the natural log of x to the third, which we can make one more change to this because we have a power rule on the third term. So for the final expansion, this will become the natural log of x plus 1 plus the natural log of x minus 1 minus 3 times the natural log of x. And that would be the best we could do to expand this. Natural log of x plus 1 plus the natural log of x minus 1 minus 3 times the natural log of x. All right, one more for expanding. Then we're going to go the other way. We're going to condense. Because you can also use these same properties to condense an expression. It's just working in reverse. So let's say we have the natural log of x to the fourth times the square root of y all over z to the fifth. So they're throwing a lot at you. You're going to have a product rule, a quotient rule, and a power rule. You have all three of them at work. Well, it might help first if we can write that y in terms of a power. So this will become the natural log of the quantity of x to the fourth, whoops, not 1/4, x to the fourth times y to the 1/2 all over z to the fifth. All right. Well, now we can expand this. In the numerator, you'll have two products. So this will turn into the natural log of x to the fourth plus the natural log of y to the 1/2. Now, in your denominator, you have that z to the fifth, so this would end up becoming minus the natural log of z to the fifth. And then for the final part, we have a power rule. So this will end up becoming 4 times the natural log of x plus 1/2 of the natural log of y minus 5 times the natural log of z. So that would be the exact expansion of all this. Now we're going to go in reverse. We're going to condense expressions. We'll start out easier again and gradually get a little more complicated. So instead of expanding, for the next several exercises, we're going to condense the expression into one single logarithm. So let's condense the expression. All right. So we'll start out easy. You have the natural log of x plus the natural log of 4. The goal is to condense this into one logarithm. Well, what does the sum of two logs relate to? It relates to the product rule, right? So this would be the same as the natural log of x times 4, or simply the natural log of 4x. That's what it will condense into, the natural log of 4x. That one wasn't so bad. Alright, let's see. We have log base 4 of z minus log base 4 of y. So we got log base 4 of z minus log base 4 of y. Let's get this into one logarithm. So what does a difference of logs relate to? That relates to the quotient rule, right? So we could write this as log base 4 of z divided by y. And that's what you would get. For if you want to turn this into one logarithm, you would get the log base 4 of z divided by y. Alright, let's see. You have 2 times log base 2 of x plus 3. So you have 2 times log base 2 of x plus 3. So whenever you have a coefficient on a logarithm, what does that relate to? That relates to the power rule for logarithms, right? This would be the same as log base 2 of that x plus 3 raised to the second power. And that's exactly what that would turn into. Log base 2 of that x plus 3 raised to the second power. Alright, we have half of the natural log of x squared plus 4. So we got half of the natural log of x squared plus 4. Well, you have another power rule. This would be the same as the natural log of x squared plus 4 raised to the 1/2, which we could rewrite one more time as the natural log of the square root of x squared plus 4. It would condense into the natural log of the square root of x squared plus 4. Alright, let's see, we have the ln of x minus 3 times the natural log of x plus 1. So yes, we have the difference of two logs here, but let's look at that second term. So you have 3 times the natural log of x plus 1. Wouldn't that be the same as the natural log of x plus 1 raised to the third? So this would turn into the natural log of x minus the natural log of x plus 1 raised to the third power, which now we just have a difference of two logs. We can condense this into one log because the difference relates to the quotient rule. This would become the natural log of x divided by the x plus 1 to the third power. And that would be to get a single logarithm. The natural log of x divided by x plus 1 to the third power. Alright. The natural log of x minus 2 minus the natural log of x plus 2. We just have a straightforward difference of two logarithms, so you'll just apply the quotient rule. This would become the natural log of x minus 2 all over x plus 2. That would be what we would get, the natural log of x minus 2 over x plus 2. Let's see here. a little bit higher, a little bit more difficult. Natural log of x minus 2 times the quantity of the natural log of x plus 2 plus the natural log of x minus 2. Alright, so this has just changed a little bit. I think it's clear we want to start with the second term and work inside of our brackets per the order of operations. So let's ignore everything outside of the brackets. Inside the brackets you have the sum of two logs, which is the same as the product rule, right? So this would turn into the natural log of x minus 2 times the quantity of the natural log of x plus 2 times x minus 2. So we know we can FOIL that. You'll get a difference of two squares, so you'll get the natural log of x minus 2 times the natural log of x squared minus 4. So it's looking a little bit better already. But on your second term, you still have a coefficient of 2. So we can bring that coefficient of 2 and make it a power. So this would turn into the natural log of x minus the natural log of x squared minus 4 raised to the second power, which now we're just down to a difference of two logs. So this will apply the quotient rule. This will become the natural log of x all over that x squared minus 4 raised to the second power. That would be how you would condense this into one logarithm. All this turns into the natural log of x divided by the x squared minus 4 raised to the second power. Let's see now. I have two more. Alright, so we got 1/3 times the quantity of 2 times the natural log of x plus 3 plus the natural log of x minus the natural log of x squared minus 1. Well, again, I think it's pretty obvious we want to work inside of the brackets first, right? Well, for sure on the first term we have a power rule, don't we? Because we have a coefficient on the logarithm. So this would turn into 1/3 times the bracket of the natural log of x plus 3 raised to the second power plus the natural log of x minus the natural log of x squared minus 1. And again, we want to condense this into one logarithm. Well, if you look at your first two terms, you have a sum and then you have a difference. So this is going to be both a product and quotient rule. So let's make that move inside the brackets. This will become 1/3 times the natural log of that x plus 3, that would be actually x times x plus 3 squared, divided by x squared minus 1. So now we've converted this into 1/3 of the natural log of x times that x plus 3 squared divided by x squared minus 1. And for the finishing touch, we just apply the power rule. All this to the 1/3 is the same as the natural log of the cube root of x times x plus 3 squared all over x squared minus 1. So that would be the end result of all this. The natural log of the cube root of x times x plus 3 squared all over x squared minus 1. We got just one more, then we're done for the day. Alright, so let's see. We have 1/3 times the quantity of the natural log of y plus 2 times the natural log of y plus 4. Then the bracket ends there, but we're not done yet. Minus the natural log of y minus 1. So notice the placement of your brackets. Again, we definitely would like to work inside the brackets first, right? If you look at your second term, inside the brackets, you have a coefficient on that logarithm, which gives you the power rule. So this is going to turn into 1/3 of the natural log of y plus the natural log of y plus 4 raised to the second power, all that minus the natural log of y minus 1. Now, you have a sum of two different logarithms inside the brackets, which means the product rule, right? So this would end up being 1/3 times the natural log of y times that y plus 4 squared, all that minus the natural log of y minus 1. We're almost there. Now, look at your brackets. You have a 1/3 as the coefficient on that logarithm. So you're going to apply the power rule to this whole thing here, to the whole bracket, which means you're actually going to get the natural log of the cube root of y times y plus 4 squared, all that minus the natural log of y minus 1. Now all you have is just a difference of two logs, which converts into the quotient rule. So for the home stretch here, you'll get the natural log, not the national log, the natural log of y times y plus 4 squared. I'm sorry, the natural log of the cube root of y times y plus 4 squared all over y minus 1. And that would be your final answer, to condense this all into one logarithm. So that's it for the properties of logarithms lesson. Next lesson's the final lesson of this unit of the exponential and logarithmic functions unit, because we're going to solve exponential and logarithmic functions. After that, we're going to be on some trigonometry for a good stretch. So I hope everyone has a great day. Take care.